Good morning, everybody. So welcome to this class, the first class which will be based on logic. So we covered number theory in the last 3 lectures, and I was fairly satisfied with the topics that we covered. We will come back to number theory maybe after some time. And now let's explore a new domain. We are going to talk about some fundamental principles of logic, and we will understand how logic actually works in general. So what actually I'm getting at here is nothing to do with the puzzle that we discussed last time. So you might remember that I spoke about a puzzle where there were 3 aliens and all of that. So that is to do with the puzzles and logic puzzles and all of that. But we are going to be talking about the math and the logic behind the concept of logic. So there's a very confusing thing that I just said. But what I actually meant is the same thing that I said. It is studying how logic is logical. Why is it logical and how does it make sense? Logic is a very powerful tool. In fact, according to me, it is the main thing that is the fundamental structure of almost all concepts in math. For me, there are 3 things usually in math that I mostly see. It's either logic, or it's arithmetic, or it is some data analysis. So these were the 3 things that I would like about math. But I think logic is one thing that is the foundation stone for almost anything that you build in mathematics. In fact, I would also say that if a concept is not logically making sense, it is very difficult for it to be, believable in mathematics. In English or in, let's say, history or in chemistry, there could be some things which might not be logical. Like, for example, I'd say, why is CUT pronounced as cut, but PUT and pronounced as put? So that might not be exactly logical in the mathematical sense, but it has got its own meaning in language. But in math, everything has to be perfectly logical, right? Exactly logical. If you define a theorem, it has to hold true for almost all scenarios. If you make a conjecture, it has to hold true. The axioms which were made by Euclid and some statements given by Euler and some of the works done by Aryabhatta and all these guys, hundreds and thousands of years ago, the logic behind those things should also stand very firm today in 2020. It's not like a scientific field, let's say, where somebody discovers the electron and they claim that it is the smallest particle and they're given a very good prize, sometimes even a Nobel Prize. And then few years later, they develop on that and they say, hey, no, actually there's an atom which is smaller than that. And then you say, oh no, inside an atom there are other things. There's a nucleus, there's the proton, there's neutron, there's electron. And then somebody says, oh no, there's actually quark, and now there is quantum thing. So there is no saturation point for discovery. You can keep improving the past in science, basically. That's what it is. But in math, if somebody proves something, let's say 200 years ago, the proof will have to stand even today. You cannot really improve on it. There are some things, like, for example, the prime numbers, the largest prime number that is in the world. You can get a larger prime number, but that is not exactly what I'm talking about. I'm talking about the fundamental principles. Even in a subject like philosophy, which is highly logical, there are some concepts which change over time. You start with one philosophy and then somebody gives a contradiction and then somebody comes up with a better philosophy. The same thing happens in chemistry. It happens in many things. Technology is the best example, because in 2008 or 2007, when the first smartphone or the iPhone was made, people believed that was the smallest possible device that you could have, or the largest possible memory that you can fit into a memory storage space, or the best speed that you could achieve. But every year it's getting better. People are sending rockets to space. There's technology that is able to almost predict how many galaxies there should be in the universe, or how many stars should be in the Milky Way. So amazing things are happening. It develops. But in math, if you logically prove something, then it will always be true, no matter what. People can discover new things, but they will never be able to say that this proof is wrong, or this proof can be better. No. So it always stays. So the thing about math and the thing about logic is that basically there are only 2 things possible. Either it is right or it's wrong. There's very, very minute amount of things that are neither right nor wrong in mathematics. Almost everything should only have one answer. Let's take the thing of what do you say, the concept of, let's say in philosophy, there's a question as to, are there aliens, or you say, are there other planets that have water? We don't know. You cannot say yes, you cannot say no. And it need not even be one of the two answers. It could even be some other answer which we don't know. It could be that there's a different kind of water that we think is not water, but later we think it is water. So all such grayish answers are possible. But in math, let's say the conjecture that we spoke last time, that is the Goldbach conjecture, right? There's only two possibilities: either it's correct or wrong. It cannot be that people think it is correct, then people think it is wrong, and then again they think it is correct. So once somebody gives a contradiction to any conjecture in mathematics, that conjecture is wrong. It is logically falling apart, and it will never again be correct. And if once somebody actually proves something to be correct, it will always remain correct, unless there's a problem in their proof. So that is their mistake. But what I'm saying is, if the proof is actually correct. So we will start our journey in logic by talking about a very simple fundamental concept which I think most of you are familiar with. It's called the truth table. So we will study the basic concepts like truth table, and then we will see how we can apply that in some day-to-day sentences and language and things like that. But we'll start with the truth table. So I'm going to share my screen. So what exactly is a truth table? For those of you who do not know it, just okay. So this is a table that you create in which you assume the true value and the false value of a given situation, and you list all the possibilities that are there. Okay. So for example, the simple truth table is the negation truth table, which is called the not table, or negation. Negation is the reverse of everything. For example, if I say that tomorrow is Sunday, then the negation is that tomorrow is not Sunday. Or if I say that I am a boy, the negation is I am not a boy. So for everything you put a not, right? That is the meaning of this negation concept. You can also sometimes say that the negation of I am a boy could be that I am a girl, but that is in terms of English. But let's say you did not know the meaning of the word boy, or you did not know the meaning of the word girl, then what would happen is the only negation that you can do is put the word not. In fact, the very interesting thing is, when a child is growing up, when it's about the age of 2 or 2.5, around that age, when it first learns language, one of the experiments that a toddler would do is test the power of no. So when a child is 1 year old or 1.5 year old, it will almost do anything that it is told to. So if you tell it to say ba ba ba, it will say. If you tell it what's your mother's name, it might mutter something. If you tell it to walk. But once it understands little bit, it starts thinking logically. It says, hey, what if I say no? So if you tell the child to do something, it will say, no, I will not do it. Or if you ask the child something, it will reply in a contradictory sort of a way. So that is the first signs of the human mind developing. One of the reasons why we are such an advanced species, although I know that all animals are equal and animals have a lot of amazing characteristic features which humans do not have, like for example emotions and things like that are also found in animals. But the one thing that is different is the ability to think in a creative manner. If you think about the human species, in 1975, what the humans were doing, if you compare it to what the humans are doing now, it's an exponential growth. In fact, that growth is so much that every year it almost is a double of it. The technology or the buildings or the cars or anything that they do, or the scientific discoveries happening in some lab somewhere in England or America or wherever in India, these things are proof that the human mind can think in a very, very abstract and creative way. And that is one difference between humans and other animals. If you look at an animal species 2000 years back and now, it's almost the same. Biologically, there might be few differences, but the way they converse, what they eat, where they go, it's almost the same. But if you think about human beings, 2000 years back, they did not know how to travel from one country to another, and today they can do it in less than a day. They would not know to talk any other language but one language, and now there are more than 1000 well-known dialects all over the world. So the not negation, to negate something, is one of the first things that a human mind does. So let us understand what is the truth table of not. It's a very simple thing. So when we talk about logic, we'll only deal with two situations. One is true, the other is false, right? As I told you, there is nothing called true or false, which is, either both true and false or something. It's either true or it's false. So what this not table would do is, if you give true as the input, it will give false as the output. If you give false as the input, it will give true as the output. So those of you who understand functions, if I say that f of x is something, what does the function do? Whatever value you give for x, it will do the value. So if I say f of x is equal to 3x, any x value that I give, it multiplies it by 3. Or if I say that f of x is root x, any value of x that I give, it takes the square root. So here you think of this as a function where any value that you give will be negated. So I'm going to make two columns in this table. One is input and the other is output. Here, if I say the input is true, the output will be false. If I say the input is false, the output will be true. And now we will try to make some binary sense of this. Instead of saying true or false, I'll say 1 and 0. I'm pretty sure all of you are aware of these concepts, and please pardon me if I'm going a little too slowly. I just want to touch upon all the points. Let's do it this way, right? So if your input is 1, your output will be 0. If your input is 0, your output is 1. So that's a very simple truth table. It's just called the not table. Okay. I sincerely request all of you to not message anything much when this is going on. You can ask me questions later so that I can just stick with the plan. I will give you examples very soon, but let's go to the next table, which is called the OR table, where what the goal is basically, it's not just one input, you'll have two inputs. And you want to see if either of those two, at least one of those two, is true. So the example in the real life situation is, let's say you decide to, let's say my situation, right? I want to travel to India, let's say. Now, if I want to travel to India, there are two conditions. One is that it should be safe to travel. That is, there should be no virus in the air. And the other is there should be flights available. Now, in this situation, I cannot actually apply the OR condition, because it is not enough for me if either one of these situations is working. I want both those situations to be working. So that is not an example for OR. An example for OR is, let us say, I will stay at home if it is raining or it is dark. One of the two situations. If it is raining, I'll be staying at home. If it is dark, I'll be staying at home. And even if one of those things is there, it's fine. It could be raining and it could be very bright, but I'll still stay at home. It might not be raining, but it could be dark. I will still stay at home. It could be raining and it could be dark. I will still stay at home. So let us create this table. This is the input. This is the output. So now we'll have two inputs. The first input is both are 0, which means both my conditions are 0. So there is nothing there for me. So it means it was not raining, and it also means that it was not dark. So I will not be staying at home. But let us see what happens when one of the conditions is true. The output is 1. I will stay at home. What if the first condition was true and the second condition was false? Output is still 1. Even if both the conditions are true, the output is 1. So this is the OR table. Remember, guys, in the example that I gave you, if I stay at home, then it means 1. If I go outside, it means 0. So, and if it is raining, it is 1. And if it is dark, it is also 1. So in the first case, it is not raining, it is not dark. So I'm not staying at home because I can. In the second situation, it is not raining, but it is dark. So I'm staying at home. Then in the third situation, it is raining, but it is not dark. I'm still staying at home. Sorry, yes. And in the last case, it is raining as well as it's dark. Definitely I'm staying home. So this is the OR table. The third table, which is pretty much the first example that I gave you before the raining example, that is the example of me traveling to India. In this situation, we want both our inputs to be positive. Both of those conditions should work. So if it is 0, 0, no chance. Definitely the output is 0. If it is 0, 1, output is still 0, because I am only looking whether there is anything that's a problem. There could be other things that are fine. Let's say there are flights, but if it is not safe, I cannot travel. Now let us say that it is safe to travel, but there are no flights. Still cannot travel. So an AND situation of logic will give you the answer as true only if both your inputs are true. So it's a lot stricter condition as compared to the OR situation, right? Let's say that an animal is, a life form is classified as an animal if it has a digestive system and it has the ability to reproduce. So let's say these are the two conditions. So you use the word AND. We don't use this thinking about the AND gate or thinking about logic or thinking about math. But in our day-to-day life, whenever we use the word AND, we are stressing upon the fact that all the conditions should work. So that is why, so if somebody says to go to play, you have to finish your homework and you have to do the dishes. Then it means, hey, you might have done your homework, but until you do the dishes, you're not going out. So you have to do both of them. But if it is an OR condition, you can, if you want to go out to play, you can either finish the dishes or you can do your homework. So that's a lot more lenient approach, right? So when there's an OR condition. Now, because we know these gates, I'll introduce you to two other gates, which are, I'm using the word gate because sometimes these concepts are introduced through computer science, because if you're making a circuit and you have a gate, so basically it's like a traffic system there. And if you're sending the electricity from one wire and not sending from the other wire, so then it's OR gate, AND gate, and things like that. So if both your things are both of them are having the on switch, then the bulb will glow. So I mean, we don't have to go into that, but that's why I'm using the word gate. But let us say the logic symbol AND and OR, because we know this. Let us use this first gate, okay, just ignore if I say gate, that's okay. So the first gate, input output, which is negation, let us use that concept to these other two gates. Now I have this situation of OR, right? How do I negate this OR? How can I give you the output such that it will be the reverse of OR? So that situation is called a NOR gate, right? It's the N is added because it is not OR, so it becomes NOR. And what happens is the output just changes. So wherever there's a 0, it becomes 1. And wherever there's a 1, it becomes 0. Right? It's a NOR symbol. If it is 0, 0, it's 1. If it is 0, 1, it is 0. If it's 1, 0, it is 0. If it's 1, 1, it is 0. So for the NOR gate to give you the output as 1, then both of them should be 0. Why is that? Because even if one of them was 0, then the output of OR would be 1. So the output of NOR would be 0. NOR is just the negation of OR. So now let us see if we can do the negation of AND, and no prizes for guessing, it's called NAND because it's not AND, and the output just changes completely. Now, here's the thing, guys. Can we as a team try to come up with an example for NOR and NAND in a day-to-day scenario? I don't want anybody to type anything. And genuinely, I don't even have any ready-made examples. So even I'll have to think. Let us think for a minute and see if we can have an example of NOR and NAND. in a day-to-day situation. Let's think about it. Okay. So I have an example for NOR. Let me tell you what this is. Let us say 0 stands for healthy and 1 stands for not healthy. That is the input. And these are the kids of a parent. So there are 2 kids and 2 possibilities where each child can either be well or not well. And the output, if it is 1, it means the parent is happy. If it is 0, it means the parent is not happy. So remember, for the input, 1 means not well, 0 means well and healthy. So that is that for input. For output, 0 means sad and 1 means happy. So when both the children are not well, when both the children are well, 0, 0, parent is happy, 1. When one child is sick, but the other child is healthy, parent is sad. When the first child is sick and the second child is healthy, parent is still sad. Both the children are not well, parent is definitely not going to be well. So for the parent to be happy, the only situation is where both the children are well. Do you guys notice that the NOR is just a different version of AND? It is same as AND, but it's a little different. Because the AND, for it to be 1, both the inputs have to be 1. Everything else is 0. For the NOR to be 1, both the inputs have to be 0. Everything else is 1. Everything else is, both the inputs have to be 0. In any other situation, the output will also be 0. So the NOR gate is very similar to the AND gate. And this NAND is very similar to the OR, because the OR will be 0 only if both of these are 0. Everything else is 1. The NAND will be 0 only if both of them are 1. Everything else is 0. So you can technically use the same examples for OR as well as NAND, but you just have to change the statements. You change the variable. You say this means 1 and this means 0. Or you can use the same example for AND and NOR, and again you change the variable. You say this means and this means 1 and this means 0. So they're very closely related. Shreyan, I hope you understood my instruction where I told people that they have to not type anything unless it's a doubt. So now this OR, we will do another exploration of this OR, and then we will move on to some other things. We'll stop with the gate. But this OR has one clause which can be changed. In a day-to-day situation, whenever we say OR, we take it for granted that either the first one or the second one, if one of them is fine, then we are happy. So that's what we mean by OR. But it could be a scenario where we want only one of them to be fine. Let's say I am driving a motorbike and I have a back seat empty, and I have 2 sisters. I tell them, I can only take you or you. In this situation, this 0, 0 is 0. So let's say both of them are not coming. No one is there on the bike. But if the second sister wants to come, then yes, she's coming. But if the first sister wants to come, then she's coming. But if both of them say they want to come, then that is not 1, because there is no place for both of them. So in that situation, this fourth situation of both the inputs being 1 gives the output as 0. So it's not enough if at least one of them is 1. We want only one of them to be 1. It's not even at most, because if you say at most, then even 0, 0 should be 1. Understand? We want one and only one input to be 1. So if both the inputs are 1, the output will be 0. So this is a situation of an exclusive OR, and this is very useful in mathematics. When we sometimes talk about proofs, we do not want all the conditions to work. We only want one condition to work. If both the conditions are working, then it could be a problem. This is a example of exclusive OR. It's called XOR. Okay, so it's a little non-intuitive in some situations in day-to-day life. Yes, so one more thing. You can either have an ice cream for dessert, or you can have chocolate for dessert. You cannot have both. So you can only choose one, right? So in our day-to-day conversation, we use OR very conveniently. We use it for exclusive OR, and we also use it for this. This is called inclusive OR, where both ones is still 1. Okay, so that difference should be noted. Okay, tell you one last thing. It's called implication. This is one of my favorite things. And next class, when we talk about some arguments, which is again my favorite thing, we will be discussing about what sort of argument is actually logical, what sort of argument is illogical. So it's important for people who are going into debate, or people who want to, just fight about some random things. These days there are so many issues coming up. Almost every day there is something or the other that happens in some part of the world. And on Twitter and Facebook and all these social media platforms, people are just randomly arguing and just, changing what they say. So what sort of argument is considered good or valid or invalid? So we'll talk about that next time. But for us to understand that, we will have to understand the meaning of implication. This implication is a symbol which all of us use in math, and it looks like this. Okay. What it means, just a second, guys, just hold on. For some reason, the laptop was overheating, so I just had to kill a program which was running in the background. It had to do with RN numbers, but now we cannot do anything about that. Okay, now I don't know where this file is. Just give me a second. Okay, so in any case, I can talk when I do this. So what is an implication? Implication is, can we decide one situation based on the outcome of another situation, right? So this implies that. What is the meaning of this implies that? So this is the implication symbol. Sometimes at the end of a proof, we put that, right? Oh, so has happened. Thus, this is what is implied. So an implication works in a very simple way. There are two sentences, and let's first make the truth table of them. Now I'm going to use true and false, just to give you a better sense of this implication. So let's say false and false, then it is false and true, then it is true and false, and the last situation is true and true. This is a very non-intuitive concept, so pay close attention and understand the logic behind this. This first sentence is used to decide whether it can imply the second sentence. So there is one sentence and there's another sentence. We want to see if the first sentence can imply the second sentence. This works in a almost crazy way. So if the first sentence is false, the logic is that the second sentence can be anything, but we consider the implication valid. Which means, if the first sentence that we are talking about is itself a wrong sentence, then that wrong sentence can literally imply anything in the universe, because that sentence itself is wrong. So we don't care what the second sentence is, whether the second sentence is true or the second sentence is false. The very fact that the first sentence is false means that the first sentence can imply the second sentence. So if I say that my first sentence is an apple is an animal, okay, an apple is an animal, that's my first sentence, complete rubbish. An apple is an animal. Now my second sentence could be an orange is an animal, which is also garbage, but it could also be that Donald Trump is the president of America. Now the first sentence, because it is false, it can imply anything. So I can say, oh, because the apple is an animal, the orange is also an animal. It might not make sense, but logically it is true because the first sentence is false. It can be used to imply anything. I can also say, because the apple is an animal, Donald Trump is the president of America, which is still a logically proper argument. But if the first sentence is true and the second sentence is false, then you cannot imply. Let's say the first sentence is I am a boy, and the second sentence is I am flying, which is false. I hope you can see that. So I cannot say, because I am a boy, I am flying. That doesn't make sense, because the first sentence might be true, but because the second sentence is wrong, I cannot say that the first sentence implies the second sentence. But if the first sentence and the second sentence both are true, then obviously it's possible. So I will not waste time convincing you that, because if both the sentences are true, they can imply each other. So because Donald Trump is the president of America, the water is colorless. I mean, it might not make sense, but it is logically correct. You can use that form of argument. Let me tell you why. So we are going to do a detailed analysis of arguments in the next class, but I'll quickly give you a trailer to that. If you're investigating a crime, let's say, you find two things, and one of them is a false evidence and the second one is true. You can do the implication because of the false and the true. That's fine, because the first thing itself is false. It doesn't tell anything. You can use it to understand whatever you want. It's left to you. You can say false implies false. You can say false implies true. And if the first evidence was true and the second is also true, you can also say that this implies that. But if the first thing is true and the second thing is false, then you cannot say that this implies that, because the second thing is false. So you might ask, hey, if the second thing is false and this is the output is false, why is it that in the first situation when both of them are false, there is implication? Because both of them are false, you can say that this implies that. That's fine, because you don't even know anything about them. They're complete nonsense, and you can use their relationship the way you want to. It is logically going to make sense. Now it's a different matter whether it will be useful in day-to-day life, whether it will make more sense than just logic. But logically it is considered okay when false implies false. That is, the output will be true. Okay, so this is the meaning of implication, and we are going to study more about this next time. So for now, I will stop the recording and we will go to the test. Thank you guys. I hope you enjoyed.